In this problem, we are to determine I1, I2, V1, and V2 in this circuit. For V1, V2, I1, and I2, I've indicated an arbitrary assumed direction and polarities of the voltages and currents. After we go through the process of setting up the transformer variables and solving the equations, a negative value for any of these variables will indicate that our assumptions should be reversed. You will have noticed that I have assumed a current direction flow. If this was a DC circuit, this assumed direction is obvious. However, when dealing with AC, and it is a little less obvious because, of course, the current is reversing every half cycle. In AC circuits, current direction is defined as the direction that current is flowing in the positive half cycle. That produces a voltage drop, positive to negative, in the resistive elements of the circuit. In this way, once a current direction is assumed, then the next step will be to mark the polarities on the resistive elements. The supply voltages are given along with their polarities. The transformer voltage polarities are also assumed. After we go through the process of solving the equations, a negative value for any of the assumed values or variables will indicate our polarity or direction assumptions should be reversed. The equations are now derived using Kirchhoff's voltage law for this network, which states that the voltage drops around a circuit must equal zero. Because there are two currents, there are two Kirchhoff voltage law equations. I1 times 1, the voltage drop across the 1 ohm resistor due to I1, plus 1 at 0 degrees due to the voltage drop of the 1 volt power supply, and minus V1 due to the voltage drop of the transformer. I assumed the polarity of the to be going from negative to positive, therefore the voltage drop is negative. The sum of all these voltage drops must add to zero. On the other side of the transformer, 3I2, the voltage drop across the 3 ohm resistor due to I2, plus 2 at 0 degrees, the voltage drop due to the 2 volt power supply, and minus V2 due to the voltage drop of the transformer. Again, I assumed the polarity be going from negative to positive, therefore the voltage drop is negative. The sum of all these voltage drops also must add to zero. We can equate the variables V1, V2, I1, and I2 based on the ratio and polarity of the transformers and get minus V1 divided by V2 is equal to 1/2, and that makes V2 equal to minus 2V1, and I2 divided by I1 is equal to 1/2, which can be rewritten as I2 is equal to 1/2 I1. Now, taking this equation, we can substitute for V2 and I2, and at the same time simplify it by removing the angle designation because it is either 1 or 180 degrees, which is the same as multiplying by 1 or minus 1. Taking this equation, I am going to simplify it again by removing the angle designation. Moving it down here and multiplying both sides of the equation by 2, we have 2I1 plus 2 minus 2V1 is equal to 0. In order to remove one of the variables, in this case V1, I'm going to add the two equations together, and that leaves us with 7 over 2 times I1 plus 4 is equal to 0, or 7 over 2 times I1 is equal to minus 4. In terms of I1 is then equal to 4 times 2 divided by 7, which means I1 is equal to 1.142 at 180 degree amps. We can now take I1 and substitute it into the other one of these two equations and solve for V1 and get V1 is equal to 0.142 at 180 degree volts. We can plug the values of I1 and V1 into our previous equations for I2 and V2. Simplifying the right-hand side, we get the solution for V2 and I2. We can see from the angle designation of 180 degrees for I1 and V1 that our assumed direction for the current and the polarity of the voltage is wrong, so they both must be reversed. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure you're not left in the dark when the next storm hits. Here are some trusted resources to help you prevent power outages at home. 𝐃𝐈𝐒𝐂𝐋𝐀 Canada at this web address. Bluetti Canada at this web address. Bluetti USA at this web address, and Bluetti Australia at this web address. And finally, EcoFlow may be found at this web address. And for those of you in Australia, here is an added bonus. Bluetti has just come out with their newest fleet edition, the Apex 300. It can put out 3,840 watts for 2,764 watt hours. It has 120 volt to 40 volt dual voltage output and is expandable up to 58 kilowatt hours at 11.52 kilowatts. With the Bluetti app, you will receive real-time weather alerts. This unit charges at 30 kilowatt solar or 11.52 kilowatts with an auxiliary generator. It powers HVACs, electric vehicles, and heavy-duty loads, and it pays for itself in as little as 2 years. In order to get more information and take advantage of this special offer, simply go to this web address. You can also obtain an exclusive offer or a 10% discount by using this code, 𝐴PEXAFF10. And not to be forgotten, for those of you in Canada, here is an added bonus. In order to get up to 50% savings on some of 𝐃𝐈𝐒𝐂𝐋𝐀's products, simply go to this web address. In addition to any price reduction at this time, you can realize an extra 5% discount by using the above email address in combination with this code, DEAL5. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.